This is Shomakrai Chaudhary, and from IUCAA, we are starting off on yet another of our Thursday colloquia, which we have been doing from April. As you know, we've now moved to every other week instead of a week, every week. And please look at our site for various of the menu we have in store for you in the coming weeks. Today, I'm so happy to invite Dr. Reinout van Weeren from the University of Leiden. He's at the faculty of the University of Leiden in the Netherlands to talk about something that is very close to the hearts of a lot of us here, both in IUCAA and in NCRA across the road, on radio observations of well, I won't give away his punchline, but it's the largest particle accelerators. Reinout was of course a PhD student at Leiden before he moved on to the Harvard-Smithsonian Center for Astrophysics, first as an Einstein Fellow and then as a Clay Fellow. Has done quite a lot of work on low-frequency radio observations of clusters and all kinds of things. I first met Reinout actually in the control room of the GMRT. There were at least two occasions when we were observing together many years ago, my coming in and taking over observations from him. And so I've known him from then, and we've collaborated on various things, written papers together. So I'm very happy to see him here. And he's from the very beginning been also in charge of looking after a lot of the frontline work with LOFAR as it grew from being only a sort of a small station to this large array that is working now. So I'm over to Reinout to talk about the universe's largest particle accelerators.
Thank you, Somak. Hi all. So nice to sort of show some of the things we have been working on in sort of the Lovar collaboration, and a bit sad to not to visit to India. So, but I hope to at some point again maybe see some of you in person, maybe at the GMRT or at IUCAA or NCRA, sort of in the Pune area. So this is sort of work what we have been doing with a quite big group of people, focusing on radio observations of large-scale structure, with a lot of people involved, and I list them sort of here. And these are mainly people from the Lovar sort of cluster surface working group, including a lot of PhD students, and I will highlight some of the work they have been doing. Okay, so let's start with sort of a picture of large-scale structure. This is a kind of old simulations already, but sort of nicely shows sort of the large-scale distribution of dark matter in our universe. And this dark matter is distributed in sort of filaments and sheets. And we also, of course, have voids. And at the nodes of these filaments, what we find we have galaxy clusters. So galaxy clusters are sort of the largest gravitationally bound objects in sort of the large-scale structure of the universe. And what we have learned sort of the last 20 years, I would say, this is quite a long period, is that we can sort of observe these structures, of course, in the X-rays. That's a very important wavelength band, where we see the hot thermal plasma of these structures. But we can also detect radio emission on sort of large scales from clusters. So that's, for example, this image shown here at the bottom left. So in red, we have some radio emission. And in blue, we have the sort of X-ray emission. And not only from clusters, but more recently, and as also indicated and hinted in the past, we can sort of also observe radio emission from regions in between clusters, so-called bridges between galaxy clusters. So these are sort of very large filaments where clusters probably in the future will merge along this sort of lines along the filament. And we also find sort of faint synchrotron emission from these bridges. So this is, of course, an important sort of realization that we see synchrotron emission from these structures, because then the question, of course, arises, how is this synchrotron emission produced? Okay, so let's first maybe introduce a little bit for the people who are not working in this specific field of galaxy clusters, sort of take the typical ingredients of a galaxy cluster. So here's an optical picture of the galaxy cluster Abell 2744. And you see typically that a massive cluster has around 1,000 galaxies. That's a very typical number. So there's all this sort of yellow spots in this image. However, the galaxies only make up a few percent of the total mass of a cluster. So a much more important component of galaxy clusters is the hot, dilute intercluster medium. So this is a very hot, tenuous, hot means like roughly 10 to 100 million degrees Kelvin gas or plasma, which permeates the entire volume of a cluster. And you can observe that with X-ray satellites. For example, this is an image from the Chandra telescope, and here you see the thermal Bremsstrahlung from this very hot plasma. And here, for example, you can already see that this particular cluster sort of has substructure in the X-rays. So it's probably undergoing some sort of merger or event, or is dynamically, in that sense, not relaxed. So this is the X-ray component. This sort of takes care of 10% of the total mass of a cluster, this sort of hot gas. And this is where most of the baryonic, so the normal matter, is in. Of course, the other sort of 90% is in dark matter, which is much harder to observe. But from the baryonic component, this X-ray emission is really sort of the main component to think about when you think about a cluster. So the galaxies are almost like just like tracer particles sort of in these objects. Now we can also look at the same cluster in the radio band. This is from the Very Large Array at 1.5 gigahertz. And what you can also see in the radio that this particular cluster also has diffuse radio emission. So radio emission that sort of extends in the same region as we can observe the X-ray emission. So on really large scales of around a megaparsec. And of course, the important thing to realize is that this is synchrotron emission, which means that we have two ingredients. We have cosmic rays, and the other ingredient is, of course, magnetic fields. And if you combine that, of course, you get synchrotron radiation. So this sort of directly sort of proves that clusters are filled, or at least some clusters are filled with cosmic rays and are permeated by magnetic fields. So it's a direct, simple evidence from this picture. Because we have magnetic fields, you can also actually sort of image them. It's not really image them, but you can map the polarization properties of some of the emission. And here you can see the electric field vectors, which are perpendicular, of course, to the magnetic field vectors of one of these radio structures in a cluster. And what we know from many studies, from this big effort by many people, is that cluster magnetic fields are of the order of a microgauss. So these are the typical magnetic field strengths. You can compare that to the magnetic field sort of on Earth, which is of the order of 1 microgauss. So the magnetic fields in clusters are in that sense very weak compared to what we are more familiar with on Earth. Despite that, of course, it's an important ingredient because without that we wouldn't observe synchrotron emission. Another important sort of ingredient to consider is that if you look at the radio spectrum of this emission, of course, it's synchrotron emission, so you typically can characterize this with a power law radio spectrum, is that the radio spectrum from this emission is relatively steep. And I show here a cartoon picture of two sort of radio spectra, one of them in green and one of them in blue. And sort of the blue one would be representative for radio emission, this diffuse emission from a cluster. And you can see that this emission is steep, meaning that it's much brighter at low frequencies. And this means that if you want to sort of observe these sources and study them, it's easier to do at low frequencies than at high frequencies. And low frequencies, I mean something like a gigahertz, typically and below. So the sort of regime where the GMRT and telescopes like Lovar or the MWA are really sort of ideally suited for. So to observe this steep spectrum sources. So this is a bit of an outline of my talk. So I will have a little bit more introduction about the particular type of sources we see in galaxy clusters. I will then go to sort of the Lovar telescope a little bit and what sort of work and surveys we are doing with this telescope. And then we'll show some of the results, some of the recent results we have obtained with Lovar. And I will hopefully, if time permits, end with a bit of an outlook. What are the sort of next steps we are currently working on, but we have not really have like final results yet. Okay, so let's first go back to the radio emission in clusters. And I go back to this sort of standard picture I like to use because we can see that the radio emission in clusters, this extended radio emission, you can subdivide it sort of in different categories. And there's one category which we call radio relics or radio shocks, in other words. These are these elongated structures which you can find on the outskirts of clusters. They're often highly polarized, already showed some polarization factors. And we think that these structures trace ICM shock waves, so shock waves in this hot gas. And there's very good evidence now that this is indeed the case. This is sort of what we learned since the last 10 years, that sort of, at least we're very confident that these things relate to shock waves. Then in the center of clusters, we have this radiohalos. So these are more lower surface brightness structures, sort of approximately following the X-ray distribution of this hot thermal gas in clusters. So these are typically more roundish. And what we think is that these structures trace ICM turbulence. There's also evidence for this, although it's a little bit less direct than I would say for radio relics. It's just much harder to measure turbulence in clusters, or almost impossible. So there are still sort of more open questions here, I would say, than for the relics in terms of the general sort of origin. It's also important to note that most of these radio relics, and at least the very large radio halos, are found in disturbed clusters. And with disturbed, I mean clusters which are undergoing merger events, are basically accreting smaller clusters or basically merging with another big cluster. Now, finally, of course, we also have radio galaxies, and they also live in clusters. So that is another sort of ingredient. So here I have highlighted one of the radio galaxies you can find in the cluster. What is typically about radio galaxies in clusters, that they're often very distorted. So often you see their jets bending sort of in the direction of their relative motion, indicating that they sort of feel the hot ICM of the cluster. So unlike radio galaxies in the field, which are sort of often nice and symmetric, radio galaxies in clusters show very disturbed morphologies. And a typical sort of cluster hosts at least a few relatively bright ones, which you can kind of quickly pick up from a relatively shallow radio observations. They're also an important ingredient in clusters, what we think, and there is possibly also a relation with some of the more diffuse structures we see, and I will go to that a little bit in more detail. In this picture, you also see a foreground, actually, radio galaxy. So in the bottom left corner, we have a sort of more classical, sort of double lobe foreground radio source, which is not in the cluster. So some of the big sort of questions in this field is still, we'd like to understand how galaxy clusters exactly form, and for example, what is the energy budget in clusters? There's still a lot of open questions here. For example, what we don't know is sort of how the ICM became to be as it is. For example, why is the metallicity distribution in the ICM sort of a certain value? Why is that rather homogeneous? What is sort of the exact energy budget available? Because that also affects the galaxies in clusters themselves, because of course galaxy clusters host elliptical galaxies and not sort of spiral galaxies with star formation. So galaxy clusters also sort of in some ways shut down star formation in galaxies. So it also links to sort of galaxy formation and how galaxies evolve, and also to feedback processes, for example, which you can find sometimes in the center of massive clusters. Then there are, of course, also many questions related to the acceleration of cosmic rays. It's still an open question, if you look really at the details, how you can accelerate cosmic rays in sort of shocks and turbulence. These are not fully understood problems. And then finally, there are many questions associated with the magnetic fields, and in particular, the origin of magnetic fields in large-scale structures, such as clusters, but also, of course, filaments. And where did these magnetic fields came from? This is still completely sort of open, I would say. Okay, so let's go a little bit, 2 slides on the radio shocks. So I said that these structures likely trace shock waves. And we know that from quite many observations of these clusters. This is one particular example, which is sort of a medium redshift cluster, which hosts some of these radio relics, and this one a very bright one, so it's a relatively easy one to study. And so what we think is that this sort of arc-like thing traces a shock wave which sort of propagate outwards after you have a cluster collision. And again, here the colors are radio in red and X-rays in blue, where you see that in the X-rays, the cluster is already elongated in the north-south direction, indicating that we have a north-south sort of merger event. And what we think is this is an image from the GMRT at 610 megahertz, so at the old GMRT. But this is sort of a very detailed picture of a relics. So we think that this is sort of the actual shock, and that this is a very large shock. So that's why I said it's a very large particle acceleration. So here we have the Milky Way sort of to scale. So these structures are really gigantic. You could see them with your radio eyes. This source, it would be a sort of a quarter of the size of the moon in the sky if we could look with radio eyes and sort of had the same resolution as our eyes, which of course we cannot. But just to give an idea that these sources are at cosmological distances, but they sort of are the size of a quarter of the moon. So they're not small sources, they're gigantic. So we think that this is a shock. So this is the arrows sort of indicate the direction of the shock wave. And that you accelerate particles sort of at the front of the shock via some prescription. In this case, I used the diffusive shock acceleration mechanism, which is sort of the standard way of accelerating particles in shocks, at least in strong shocks. So we know, for example, this is a mechanism which happens in supernova remnants. So you inject. Inject is another word for acceleration. So you accelerate the particles first, and then if you have a shock, you have a sort of the shock downstream region where material sort of affects downstream from the shock. So this radioplasma, once it is accelerated, affects downstream, and then we have the classical synchrotron energy losses and the inverse Compton energy losses. So inverse Compton is because of scattering against the cosmic microwave background. And those energy losses, we know, sort of changes the radio spectrum, and that means that the radio spectrum gets steeper because of this energy losses. So we expect also sort of a steepening of the radio spectrum in the back of these shocks. And this has now been observed in, I would say, more than a dozen clusters, and this is a very sort of ubiquitous thing to observe if you have this nice, clearly defined relics. And this is an observation of that, where you see the spectral index map, where you see the steepening in the back of the shock. And these are this synchrotron spectra, right, where you have a power law spectrum once you accelerate. So that's at the front of the shock, and in the back you sort of get this steeper aged spectrum, and that is represented with the blue colors. And then finally, if you have a shock, you have compression. And if you have a random magnetic field in a medium and you compress it, you align the magnetic field, and you get polarized radio emission. So this also sort of agrees with the picture that these sources are highly polarized because we have a preferential direction of compression. So that leads us to this polarization, highly polarized sources. I won't show that here, but of course, I said this is likely a shock. We also have evidence of a shock by looking at X-ray observation, because of course that's where we can directly observe shocks, and we can measure, for example, the Mach number from X-ray observation. Also from the radio spectral index, if we assume a certain sort of model. Going a little bit back, so again, I said that we think these sources sort of trace accelerated shocks created by merger events, and this was already proposed sort of in the 90s by Enslin et al. In 1998. And there's also been a lot of work done on diffusive shock acceleration, and also some of the earlier work was, for example, done also by people at IUCAA, at Joydeep Bagchi, for example, who also observed one of the sort of classical double relic shocks, and also in that work already hinted that this is related likely to cluster merger events. So this idea is not new, but only now we sort of have really like a complete picture where sort of every sort of observational evidence sort of falls in place, from very detailed X-ray observations to very detailed polarization studies and spectral index studies, where sort of everything has come together now, sort of completing this picture, except for one sort of final sort of open question, and that is whether we really accelerate particles using or via diffusive shock acceleration, because that is not completely clear yet, because according to theory, it's not, at least diffusive shock acceleration is not efficient if you have low Mach number shocks. And the X-ray observations of these objects indicate that the Mach numbers are relatively weak. So that means Mach number of 2, 3, or something like that. And that is not very high for diffusive shock acceleration, and leads to sort of problems to explain the sort of radio brightness of these sources. So this is a sort of open problem, is why are these sort of cluster shocks essentially so efficient in accelerating particles? They're much more efficient than sort of what the theories say. And because of that, people have come up already sort of in the early 2000s with models where we actually have re-acceleration. So we have diffuse shock acceleration, but you do not accelerate a particle sort of from the thermal pool. So that was basically from a particle which we can sort of emits radiation at X-ray wavelength, so sort of the keV energy range. But you start with already mildly relativistic particles, so gamma factors or Lorentz factors of like maybe 100, 200, 300, or maybe 1,000. Because in that case, it's much easier to sort of re-accelerate these particles back to sort of the GeV energies we see at gigahertz frequencies. And this is what we call sort of the re-acceleration model. And there's also evidence for that. This is a GMRT image where we observed a particular AGN, which we think sort of run through a shock wave, and which sort of led to sort of flattening of the spectra at the location of the shock wave. So there is sort of evidence out there that re-acceleration does take place in some clusters. And question now is whether all radio relics sort of are tracing sort of these re-accelerated electrons, maybe from radio galaxies, for example, or whether there are also relics which still sort of are accelerating particles really from the thermal pool. This is sort of the open question at the moment. Oh yeah, so this is the X-ray observation where, for example, you can do the temperature measurement across a radio relic, and you can see that there's a temperature jump at the location of the relic, which means a shock. And you can do the same with the density. Of course, you need the combination of both of them to really prove there's a shock. That has been done for quite many clusters now. Of course, this is not easy measurements. So for some clusters, it works better than for other clusters. But in quite a few cases, there's clear evidence for the presence of a shock. And then you get here the Mach numbers of around 3-ish for this particular object. Also, actually, one in the south. So I didn't talk about a sort of fainter relic in the south, but this is a symmetric sort of collision. So you get a double relic, we call this, and we have another one in the south of this cluster. Yeah, this is the Mach number, sort of the temperature jump corresponding to a Mach number of around 2 in the south. Okay, if we go to radiohalos, so radiohalos are these more diffuse structures, and they are found in merging clusters. That's sort of the first important observations, or at least most of them. And that is indicated in this diagram here, where this diagram sort of is a parameterization of the X-ray image, which lists the concentration parameter, so how concentrated is the X-ray emission, versus sort of the asymmetry, which is, or centroid shift. Basically, this image has a large centroid shift from the bullet cluster because it's a non-spherical symmetric sort of brightness distribution. And if you place them in this diagram, you have relaxed clusters in the top left corner and merging clusters in the bottom right corner. And you see that most of the radiohalos indicated here in red with red points are located sort of in this merger sort of regime, indicating that mergers are likely an important ingredient in the formation of radiohalos. And that relates to the sort of theory behind the formation of radiohalos, which is turbulent reacceleration. So also in this case, you need sort of seed or fossil cosmic rays. And these fossil cosmic rays are then reaccelerated by turbulent motions in clusters. And this turbulence is sort of increased when you have a merger event, leading to sort of the fact that there are more radiohalos in merging clusters. There are also other models still out there, but I won't discuss them here for the sake of time. But most people nowadays are sort of think that the origin is turbulent reacceleration for this cluster. And this is also has been very in detail simulated with hydro simulations, very high resolution hydro simulations, where you can track sort of the amount of turbulent energy in the ICM when you have a merger event. And you can see that that increases. Okay, so maybe sort of to finish here, the introduction, it's important to realize that for both the shock reacceleration and the turbulent reacceleration model, we need to have this sort of fossil population of cosmic rays. So this mildly relativistic cosmic rays, which sort of gamma factors of around maybe less than 10 to the 4, so around 10 to the 3, 10 to the 2. And these we cannot observe at gigahertz frequencies, right? Because at gigahertz frequencies, what we see is Lorentz factors or gamma factors around 10 to the 4, 10 to the 5. That's the typical energy or the typical Lorentz factor of an electron you can see with a very large array. To observe this lower energy electrons, or see sort of maybe the tip of the iceberg, you need to go to lower frequencies. So ideally sort of megahertz range frequencies, or even lower, but that's not possible from the Earth. So we sort of have to go as low as we could. We have to go as low as possible, and that is sort of the megahertz sort of range, or maybe the 100 megahertz range roughly. And then there are questions, of course, where are these fossil electrons come from? So what are the sources of these? And of course, another open question is, are they really there, and can we observe them? Because of course we have to test this. And that means we go to low frequency. So that's sort of my setup for going to the Lovar telescope. So as you all know, this Lovar is a phased array telescope located in Europe, with most of the Lovar station and antennas located in the Netherlands, sort of on a very flat sort of land, muddy. These things sit on the ground, so they cannot point in a classical way. You point them by phasing them electronically, and that has the additional advantage that you can look, for example, in multiple directions at once on the sky, and this is only limited by your computing power. So typically for the Lovar surveys, we observe in between 2 and 4 directions simultaneously, with a certain amount of bandwidth. So you can change bandwidth and frequency sort of freely in this phased array telescope. There's one big challenge, and that is sort of indicated here. That's the ionosphere, as you might be aware of. Ionosphere is the main problem we have to tackle in order to get high quality, low frequency radio observations. And you can sort of imagine what the ionosphere does. This is sort of a nice analogy. So if you think you are sort of at the bottom of a swimming pool or in a water, and you try to look upwards on the sky, maybe at the cloud, then you get a very distorted picture of this cloud. And this is sort of the same situation we are dealing with at low frequencies. And this water is the same as the ionosphere in the radio band. So we need to correct for all this sort of blurring and strange distortions. And that was a very hard thing to do. It's very computationally intensive, but we now can do this routinely, sort of in a pipelined way. Meaning that we can really sort of do high quality, sharp, deep imaging at low frequencies now. Also with, I would say with sort of all the low frequency radio telescopes now at the moment. And since we have that now in hand, what we are doing with Lovar is we're doing a very deep northern sky survey, which we call LOTS. It's the Lovar 2-meter sky survey. So this is roughly 3,000 pointing northern sky survey, 8 hours per pointing, and roughly 6 arcsecond resolution, and a noise below 0.1 millijansky per beam. And we are currently sort of halfway through this survey. So we have half of the survey observed and also, I would say, processed. What is publicly released is only 5% of the sky. So that's the area in green here. But we're currently working on a sort of second data release, which will significantly increase the fraction of the sky to something like 20%, at least for the public. So that will become public and with catalogs and images at some point, hopefully in 2021. And just give an indication where is this survey located in sort of survey space. So this is frequency against sensitivity. You can see that this survey is really sort of a 2 order of magnitude step compared to the current surveys in sensitivity, but also in terms of resolution at this low frequencies. And This is sort of this is the real survey. This is the real pictures. Of course, it's very zoomed out, so you cannot see details, but this is where we stand at the moment. And so you can see that we are really at 50%. So we know sort of what 50% of the northern sky looks like really in detail at very great depth at these frequencies. And you can see the galactic plane actually sort of running over this picture. This is looked from the north, from the NCP. So you can see that we have avoided the galactic plane a little bit. So we have done less observations there because it's more difficult. Just to give you an indication of what difference that makes. So this is the famous NVSS survey at 1.4 gigahertz of a typical field. You can also observe this with FIRST, which is exactly the same field, but at higher resolution. So this is the FIRST survey. It's a little bit deeper, but it misses extended structures, but it has better resolution. So 5 arcsecond. And this is what we see with LOFAR, so in the LOFAR survey. So you can see a sort of what of step we make here. You can even see it's hard to sort of exactly see the correspondence. You almost think it's a different field, but if you look closely at the compact sources, you see that actually we're looking at the same field. So this sort of indicates where we are going with the survey and what sort of the quality is. And then finally, you can also, of course, compare with the TGSS survey, because that's a very nice survey at the same frequencies, sort of a precursor in some sense in terms of depth. This is the TGSS survey of a famous cluster, which is in the survey in lots, sort of again indicating sort of the nice step we make in depth and resolution compared to previous sort of surveys. So really sort of taking it to a next level with this survey. Okay, then I go to some of the latest results on galaxy clusters. So there's already a lot of results, but I want to highlight 2 more recent works, what we have been doing. So one of them, what we have been doing is to sort of take a step back and start off asking some very basic questions. And questions as what fraction of clusters at low frequencies shows diffuse radio emission. So either the cluster has a relic or a halo or some other sort of extended, a very megaparsec scale emission. Because of course, if you go to lower frequency, that fraction might be different from what we have observed at high frequency, because now we are sensitive to this sort of steeper spectrum or lower energy cosmic rays. So the answer might not be the same. To answer this question, sort of first we looked at the data release 1 area. So this is 5% of the sky. And we systematically looked at all the Planck, Sunyaev-Zeldovic selected clusters in this area. And why this particular Planck sample? Maybe people are not aware of that, but the Planck catalog is a very nice cluster catalog because it was selected from the SZ effect. And it has a very well-known sort of selection function, which is very well understood. And in addition to that, because we have a measurement of the SZ signal, you can convert that into a mass measurement. So for each of these clusters, we also have the mass. And that is important because, for example, what we want to know is there's some famous scaling relations between radio power and cluster mass. And that's what we can then directly test if we have the mass, and we just then need the radio flux. And then we can sort of check if the scaling relation is the same as at high frequencies. So in this 5% of the sky, there are 26 Planck clusters. You can see them here. So this is the redshift and the mass distribution of this cluster. So you can see that there are clusters of various masses in this part of the sky, and also at various redshift. In particular, there are a relatively large number of higher redshift clusters in this part of the sky, sort of just by accident. It was not chosen to be like this. For that, we also had to develop some extra additional processing because the data release 1 sort of quality was not sufficient for this work. Because as I've shown in all the pictures, the diffuse emission in galaxy clusters has a very low surface brightness often. And that means you have to be really careful to properly deconvolve this emission. And also sort of remove emission from compact nearby bright sources. So for that, we developed some extra sort of software on top of the survey sort of standard pipelines to do this. And also, for example, to jointly deconvolve clusters which were observed in different pointings. Because we're doing a survey, our cluster can be at the edge of a pointing. So then we have to combine multiple pointings to get sort of the deep image. And we can do that now also with sort of joint deconvolution in imaging planes, so to really get sort of the maximum quality out there offered by the data. And here you can see an example where we go from the standard data release 2, which is not public actually even. So this data release 1 is much worse than this. To sort of this additional step on top of that, where you do this extra calibration, where you clean it up even further to get a really sort of sharp image of this particular cluster. You see there's some halo present in this cluster here. So these are sort of the results. These are 9 clusters where we see some diffuse emission in this region of the sky, just to get a rough idea what we see. So these are in all cases X-ray images overlaid with the sort of the high band antenna contours. These are the high band antenna are the ones which observe at 150 megahertz. We also have another type of antenna which observes at lower frequencies. But the lot survey is done using this HBA, this high band antennas, which is also the most sensitive band of LOFAR. So you can already see that we detect a lot of diffuse emission in these clusters. And here are some examples of particular clusters where you can sort of see what we observe. So you see a scale bar here of a megaparsec. So you can see that in many of these clusters, we really observe sort of halos and maybe relics on the sort of megaparsec scales. And again, here there's an optical overlay and there's an X-ray overlay. And this is different resolutions here. Yeah, the other good thing about LOFAR is that it has many short baselines because it has 24 stations in the core, providing a lot of baselines of around 100 meter sort of range, and from 100 meter to 1 kilometer, a little bit like the central square of the GMRT. So there are even more, I would say, more short baselines than the GMRT. So that allows for very nice sensitive imaging of extended emission. These are sort of the hard numbers which we got out from this sort of mini, well, it's a lot of work, but it was sort of a mini first investigation. So from the 27 clusters in this part of the sky, we find that 19 of these clusters show evidence for diffuse emission. So that the majority of clusters we detect with LOFAR from the Planck catalog, they either have halos or relics. So we find, for example, 8 radiohalos, 8 candidate radiohalos, and 4 clusters with relics. You can see there's sort of a mismatch between the 19 and the 8 here and the 4 here. And that's because for quite a number of clusters, we are 100% sure we see diffuse emission, but it's hard to really classify that emission precisely. So in some cases, it's sort of maybe a halo mixed with the relic, or with also some tailed radio galaxies thrown through it. So classification is definitely complicated when you have such deep images. So this is a little bit of a challenge still. We're currently working on sort of a more generalized classification scheme to sort of get agreement maybe in the sort of between people of how to classify things, because there's people typically do this sort of by eye and sort of make their own judgment call, but it's not very uniform. If we project what we now should find for the entire lot survey when it is completed, we expect to find at the minimum 200 radiohalos in Planck clusters. If we also include non-Planck clusters, because there are of course also clusters not in the Planck catalog, typically they are of lower mass, then we expect to find at least 500 radiohalos if we take all clusters into account. And this is sort of a conservative estimate because I did not include any candidate radiohalos sort of in this sort of computation here. So if all these candidates are real radiohalos, these numbers will sort of double. Now with these numbers and with the flux density of the radiohalos, we can compute their power. And we can for the first time at low frequencies investigate if we observe a sort of a relation between radio power and cluster and mass. And that is what is indicated here. So on the x-axis, we have the mass of a cluster. So you see these clusters are typically 5 times 10 to the 14 solar masses. So that's quite massive for a cluster. And here on the y-axis, we have the power, so the luminosity essentially of the radio halo. And you can see here that there's clearly a sort of relation between mass and power, so that the more massive clusters also host the more powerful radio halos. And we think this is related to the fact that sort of more massive clusters have more gravitational energy available to basically be converted into cosmic ray electrons, so that the ultimate source of the energy which goes into the cosmic ray electrons come from this sort of gravitational energy released during merger events. And if you do that, then you expect to approximately see such correlation. And this can also be modeled. There are quite some advanced models here which sort of try to make these predictions. This result, I should say, agrees with what people have found at higher frequencies. So at higher frequencies, people also have looked at this sort of relation between luminosity and mass. And this result agrees quite well. So, for example, the blue one is the slope obtained at high frequencies, and the black one is what we obtain if we fit this. And these slopes are sort of in agreement within the uncertainties. What is very interesting to note is that if you believe in turbulent reacceleration, you believe that that model is sort of correct, is that what you expect is that at low frequencies, the slope will steepen. So that's sort of a test of the turbulent reacceleration model. And we see sort of a tentative hint of that because indeed the blue slope, the blue slope is a little bit flatter than the black slope at low frequencies. But this is just tentative. It's not statistically really significant yet. So a larger sample will be required to really test if this prediction is really correct. And there are also open questions of how the slope exactly changes as a function of mass. So that slope, of course, doesn't have to be entirely constant. It doesn't have to be a perfect power law across this frequency range. So that's what we are sort of working on with larger sample. We're currently working on a sample of 200 clusters with a lot of people from the data release 2. So that will still take a sort of a 6 months to really get all fully analyzed. But that's sort of the step. So going from 26 clusters, we go to 200 clusters. So that's and that should allow us to really test this prediction. The other sort of more recent product we have been doing in sort of a large product is from a PhD student in Leiden, so Gabriela Di Gennaro. This was recently published like a few weeks ago in Nature Astronomy, is to look for diffuse radio emission in really distant clusters. So clusters above a redshift of 0.6. So I should tell here that clusters approximately formed around a redshift of 1. So if you go to a redshift between essentially a 0.6 and 1, you're sort of really at the moment when the first massive clusters really assembled. So if you go much beyond the redshift of 1, clusters did not exist. So this is really high redshift sort of stuff for clusters. And what we found is that in a sample of approximately 20 very massive, again, Planck selected clusters at high redshift, that about half of the clusters we found host a radio halo. And this was actually a bit of a surprising result because we thought, okay, we might find a few, but that we would find them in 50% of the observed clusters was a bit of a surprise. And in order to sort of appreciate this a little bit more, it's important to realize that the inverse Compton losses go as 1 plus z to the power 4. So this is the energy you lose by inverse Compton losses. So if you go to a redshift of 1, so you essentially increase the inverse Compton losses by a factor of 16. And if you simply only look at this, you would think that this radio emission would get very faint at high redshift, which is apparently not the case. These radio halos are really sort of have the same luminosities as what we observe at low redshift. And this is one example of a high redshift, sort of 1 megaparsec radio halo. This is at redshift 0.82 here. This is the full sample. So you can also see there are some clusters which do not host radio halos. But you see quite a number of clusters which, again, which show sort of diffuse emission on the sort of half megaparsec to megaparsec scale. This is quite difficult work, I would say, because this is a really high redshift. So you really need the sort of 5 arcsecond resolution here to sort of make sure that you remove all the sort of compact AGNs from the diffuse emission. And this is just to zoom in here to just appreciate it more. You can really see this is diffuse emission if you, for example, compare it to a compact radio source. So this is really emission on sort of the 500 plus kiloparsec scale. These are the X-ray overlays. And what we find is that, again, the majority of these sort of radio halos do seem to be located in dynamically disturbed clusters. And I should say that in this sample, the majority of the clusters seems to be disturbed. So maybe we are witnessing very violent merging events here. That's very well possible, maybe leading to sort of a high fraction of radio halos observed. One interesting thing is that, as I mentioned, is that these clusters were actually surprisingly bright. We didn't expect them to be so bright. And if you compute their radio power, they really have similar radio powers as the low redshift clusters. That's shown in this diagram here, where again we have the mass versus the power. And the high redshift clusters here are in yellow. And you can see that these yellow clusters really are sort of in the same ballpark as the low redshift clusters in black here. And if you think that there is turbulent reacceleration and you sort of make a toy model of what radio power you expect, then of course you have to plug in the magnetic field of the cluster, because that determines to a large extent what the observed radio power is. You find that you sort of need, again, a micro-Gauss magnetic field in order to explain sort of these observed radio powers. And that indicates that essentially these massive clusters at high redshift, they already have the same sort of magnetic field strength as clusters at low redshift, meaning that this relatively strong magnetic field, strong is of course a bit between quotes, strong magnetic fields were already in place at a redshift of around 1 for these clusters at least. I should note here that, of course, these are very massive clusters, so they also formed early. So the question is whether in sort of lower mass clusters, maybe we do see more evolution in the magnetic field. That is an open question, we don't know. We are currently following up these clusters with the upgraded GMRT, so to sort of get their radio spectral indices. That's an important next step. Okay, this is sort of a summary of the two sort of results I showed for LOFAR and sort of the general point that galaxy clusters are large particle accelerations. So we see that diffuse radio emission is very common at low frequencies, and it also seems to be common at least in massive high redshift clusters. So it's not a sort of rare phenomenon at all anymore. It does occur in a majority of clusters. And to sort of see where we are going, this is sort of the latest work, and this is really exciting work, I find. One thing we are currently doing is we're going very deep. So I said all the previous work I've shown was using the normal lot survey, which is just the standard depth, the sort of survey depth. But we also have now observations of clusters at sort of the 75-hour plus range. So this is the cluster for an example here of ongoing work of Able 2255, where we can now see, using these very deep images, that this emission extends even on much larger scales than what we observe with the X-rays. So we find diffuse radio emission around these structures sort of on the 4 to 5 megaparsec scales. So also in regions where there is very little X-ray emission. Again, we don't know why that is the case, because that again suggests there's very efficient acceleration ongoing in this very, very low density environment. And why that is the case, we don't know yet. So this is sort of an avenue we are exploring. The other thing we are doing is we're also going to lower frequencies. So as I said, the lot survey was using the HBA antennas, but we also have the LBA antennas, which observe essentially below 100 megahertz, so between roughly 10 and 70 megahertz. And by going to even lower energy, right, we can sort of hopefully see this bulk of this fossil, or go deeper in the iceberg of the fossil cosmic ray electrons, right? Because this is sort of what we see with the tip of the iceberg is what we can see with the VLA, and the high band sort of probes the first part underwater. And if we go to the less energetic component, then we really have to go lower in frequency to sort of start probing that range. And that is there's a lot of ongoing work there now to really also get a survey sort of going in this frequency range. And so these are using this low band antennas here, which look a bit different from this high band antenna stations. And just to show what progress we are making here, this is the first deep field from a famous deep field with this LBA antenna. So this is at 54 megahertz. This was sort of the previous best result, which I published sort of 5 years ago. And what we can now do with much better improved calibration, we can now make it look like this. So this is below a millijansky noise at 54 megahertz. So this is really deep at these frequency ranges. And also it shows sort of the quality we can now achieve, because the ionosphere is really challenging at this range. And this is roughly at 20 arcsecond resolution at these frequencies. And again, to sort of highlight the improvement in calibration, this is sort of the classical self-calibration on the left, and it shows the importance of direction-independent calibration to get high-quality images at sort of the 50 megahertz range. Without direction-independent calibration for the ionosphere, you really cannot really make big steps. So we're currently doing this for the first sort of part of the sky, also running a survey now with this on these LBA frequencies. And that is led by Francesco de Gasparian, who is also already working hard on all this calibration and pipeline aspects. And he's in Hamburg and Bologna at the moment. So very soon, we also will start seeing LBA results for clusters. In fact, we We already published a paper on one of the famous clusters, and I didn't discuss that, didn't have time for that. But soon we also will start doing samples using this LBA, and then we get information about all the spectra. Because we cannot get spectral information from the VLA. These sources are just too faint at sort of the very large array frequencies, gigahertz. It just takes too much time to get deep data there. Of course, we also taking data with the upgraded GMRT in band 3 or band 4, because that's also a very nice complement in terms of depth to the Lovar observation. Then finally, we are also doing something else in terms of resolution. So everything I showed you was using Lovar stations located in the Netherlands. So that's sort of all the Lovar stations located in this small red circle here, because the Netherlands is not very small. So this is roughly a 100-kilometer diameter circle. But all the data for the surveys is recorded also with stations throughout Europe. So we have many more stations, so more than which give much longer baselines. And thus much higher resolution. So with these longer baselines, if we can use them, we have the data, we can get well below the 1 arcsecond resolution, so roughly 0.3 arcsecond resolution. And in principle, we could survey the entire sky at this resolution. And the data is sitting in the archive at the moment, so it's more of a data processing challenge than taking the observations. The observations we already have. And we are working on sort of getting that running. That's a big computational and calibration challenge. But I should say that sort of this starts working as well. Here you can see an image from the LOT survey. So this is 5 arcsecond resolution of a 8C source. That's a random sort of source. And this shows what you can do. This is work by Frits Zwijn. It's a PhD student here. If you can use the Lovar international station. So you can suddenly sort of go from 6.5 arcsecond to 0.3 arcsecond. So you see what difference that makes for this particular source. So you sort of get Hubble resolution, and Hubble resolution survey if you can process this for the entire sky. And we have currently just this is sort of hot off the press, it's not published, but Frits managed to have one full field of view of a Lovar observation, which is roughly a few degrees in size, to process a full field of view at this sort of Hubble resolution. So this is 0.3 arcsecond resolution. And to do that, this is really challenging because you need, this image is roughly 90,000 by 90,000 pixels. This is one observation. So to make this image took like sort of a half year of computing time. We have already sped it up a little bit, but it's an enormous challenge. But then you can sort of, you cannot visualize this on a computer screen anymore via Zoom, but you sort of have an indication here. This is 6 arcsecond resolution, then you zoom into the 6 arcsecond here, and here you get the 0.3 arcsecond sort of cutouts of here. So this entire field of view here of this field is mapped at this 0.3 arcsecond. And at really at a microjansky level depth. So this is around 50 microjansky depth. And this is just one 8-hour data set. So we have 1,000 of them. So there's much more to go. And this again sort of highlights what we can do. So this is sort of the 6 arcsecond LOTS resolution survey. And here you go to the sort of 0.3 arcsecond resolution survey. And yeah, at the microjansky sort of level. So that's also sort of ongoing work to get this working for more fields. And this will, again, be another sort of order, well, is it almost a factor of 20 in resolution what we will win here compared to the current LOT survey. And in depth, we also will go a little bit deeper here. Because we have more collecting area, of course, with these international stations. Okay, with that, I would like to finish because I see my time is sort of up. And thank you all for attending.
Thanks very much, Reinout. It is spectacular, absolutely spectacular results and images, and many of them we haven't seen before. I'm sure there are many questions. I would ask people who will ask questions to raise their hand using the raise hand option in the participants window. There are quite a few others in the YouTube channel, which I'm going to just take a look at. But Anwar, go ahead. Yours is the first question.
Thank you. So what you said about the relation between the degree of relaxation of the clusters and radio halos, that disturbed halos have show the evidence of radio halos. Now with bigger statistics, can you make any systematic statements here? For example, you can measure the degree of relaxation from X-ray isophotes, for example, but because then, tentatively at least, this degree of relaxation can be translated into time. So does this turbulence and magnetic fields decay after the epoch of major mergers, or it reaches some more or less steady state? Probably you can start doing such things. Thank you.
Yes, that's a very good, relevant question, and actually really what we're sort of trying to work on. So because with a sort of large number, in particular with a sort of 200 cluster sample, for the large majority, actually, we have X-ray observations. So we can really quantify their dynamical states. We have very accurate masses. So we can start looking at subsamples in terms of mass, in terms of dynamical state, how that, again, correlates to sort of the occurrence rate. And this is, some of our major goals we're currently working on, to really sort of quantify these things. Because I did this for the 26 clusters. It's a bit low number statistics, but the next step is indeed exactly to quantify this number on a large sample and see if you can start seeing trends. Because is it indeed the case that if you have a more disturbed cluster, for example, the radio power is a bit higher and it decays maybe to some base level? And yeah, that is, we are exactly sort of working on these aspects. Yeah, very relevant.
Thanks. Kandu, you're next. Kandu, you had a question.
Yeah, I was wondering that if you think of this low frequency emission at high redshift, at let's say 0.7 or 0.8, whatever, then the inverse Compton will win unless the magnetic field is 1 plus z squared times the CMB field, which is about 3 point something microgauss. So it's more like 10 microgauss, it looks to me, that the field that you require for synchrotron to win against inverse Compton. And you are estimating just 1 or few microgauss. So is there something more to it, or?
Yeah, very good question. Indeed, naively, if you see sort of the same power at higher redshift and as at low redshift, of course, you have to compensate more of the inverse Compton loss, and so you need even stronger magnetic field to sort of compensate these losses. Isn't it the case, if you sort of calculate sort of the number, you get indeed somewhat higher values than just a few, maybe 5 to 10. But I should mention here that there's another ingredient, and that's the amount of cosmic ray electrons you inject, because it's not only a function of magnetic field, it's also if you can accelerate more cosmic ray, sort of per unit volume or something. If you can do that more efficiently at higher redshift, because maybe there are more sort of seed cosmic rays present. This you also have to take into account, and this is not entirely known. So that is why we think that at higher redshift, if cosmic rays were supplied by AGNs, the sort of seed population, then you might have more of the seed population present, because there is a higher fraction of active AGNs at higher redshift. So
okay.
This we don't know exactly. So this is also an ingredient which goes into this, and that's why we're not exactly sure. We sort of have a hand wavy sort of number of maybe between 1 and 10 microgauss, but it's hard to really go much more precise and say, okay, they're clearly much stronger than at low redshift, because we don't know this sort of other ingredient, and that's the amount of cosmic rays in this cluster. Because there's also, yeah, if you can inject more of them, then you have another sort of balance.
Okay, thanks. Yeah.
Kandu, question to you. I mean, following on the discussion we were having just before the talk started, I mean, what do you expect in theory?
Well, that depends upon the amount of turbulence. For the magnetic field, it depends on the amount of turbulence that you can induce. And it's also plausible that you will have more velocity of turbulence will be more at higher redshift, because things are just forming and all that. So yeah, it's an interesting question, of course, yes.
We did take the sort of turbulence as a function of, the amount of turbulence as a function of redshift. We looked at that. That was sort of included in the model. But of course, individual clusters can also differ to a great amount. And the question is, maybe the clusters we are looking at the moment are from Planck selected. And okay, Planck has a certain also its own selection function. And if somehow we are selecting sort of really powerful mergers, then indeed the turbulence could be sort of elevated above an average cluster population. And that's why we then suddenly see maybe more halos. Although there's a lot of discussion in this sort of field of cluster selection with Planck, and the sort of Planck people, they do not agree that we have a higher percentage of mergers here. They say Planck sort of selection is not really biased against that, but other people sort of disagree a bit here. So I think this is an open question to really understand. Yeah, this.
Very interesting.
Go ahead. Thanks. Next question's from Pratik Sharma. Pratik, go ahead.
Yeah, thanks. That was an excellent overview talk. So the question I had was, so you mentioned the turbulent velocity required for particle reacceleration to create these radio halos. So in future, there will be these X-ray instruments with very good spectral resolution. So are there any predictions for those? For like, you have a whole range and classes of radio objects, and you have models which say that this guy has more turbulent velocity and this has less. So it is perhaps a matter of time that these can actually be tested. So is there any work out there which does this exercise?
Oh, you're asking a very good question, something that's on my wish list. Indeed, in the future, with, for example, the Prism satellite, although that's a bit for really nearby clusters, so that's not, you cannot do a sample with that, but also with the Athena satellite, we can indeed get this sort of high resolution spectral information and look at the turbulent broadening of lines. So we really will get precision measurements of turbulence in clusters. So that will be coming in the next decade, hopefully. I have sort of, because I'm not a theoretician, I have sort of asked this question to a theoretician, and they say it's not entirely trivial, because the turbulence which is causing the acceleration is sort of on a micro kind of scale, and the turbulence you observe with sort of an Athena satellite is really on sort of the kiloparsec, or on a large scale. Yeah, you have a big pixel, and a pixel is still sort of maybe 100 kiloparsec in size. But it is indeed sort of expected that we hope to see a correlation that you can measure the amount of turbulent energy and then translate into that sort of an observed radio power. But I am not aware that these models are really out there yet. It's just that these people have not really done that yet because no data exists. But I hope they get motivated by that and sort of make more detailed predictions so that we can really test this. And those predictions are not there yet. So there's room for people working on this to hopefully come up with this sort of more detailed predictions.
GRISM is supposed to come online in 2 years, so it's not a long time.
Yeah, so I'm not aware of that there are any detailed predictions yet, but I do expect these hopefully will come. And because then we can really do some tests. Ideally, they do the predictions before, so we can. That's always more fair, because afterwards people can always make things work.
Theories can always say, "Oh yeah, this is what you'll get." Okay, thank you.
But they're not there yet. Yeah.
Hello. Hi, Reinout.
Hi, Ruta.
So with LOFAR, how deep are the upper limits, and what do the non-detections with LOFAR are now telling about the hadronic model or the state of, let's say, the seed relativistic electrons in those clusters?
The honest answer is that we, for the large sample, we have not done a full upper limit analysis. It does seem the case, though, that there will not be so many clusters with upper limits, at least in my sample, because the ones where I did not detect radiohalos were actually the ones with bad ionosphere conditions. So usually when you have good data, you see something, at least in the sample I had. So it's not clear yet what the exact numbers will be in terms of the non-detections. That requires a larger sample. And for the hadronic models, I guess that could sort of set a base level at some point where also maybe the hadronic emission should be present, because at some level there should be hadronic emission, because this theory is still, it's a correct, I think, theory. The question is at what level will this hadronic emission be? And I guess this sort of upper limits we set there will hopefully tell us, but we don't have these numbers yet. And it will be maybe hard to really prove it will be hadronic emission. That's always, of course, hard, because maybe if you have a spectrum, because maybe hadronic emission has a different spectral index than if you expect turbulent, maybe reacceleration. But yeah, we don't have these numbers yet, but that will be something which should come out of this. Yeah.
Thank you.
Thanks. There doesn't seem to be more questions, but I'll have a last question for you, Reinout. I mean, and just a very general picture, even at low redshift, you started off by showing, for example, the Bologna group's famous plot of interacting clusters, the degree of interaction, and their relation with the kinds of radio halos or such diffuse emission, etc. Right, and then you later on made the comment that the way you're getting over 90% of all clusters seem to have some kind of a
so this plot is not correct at low frequencies. it's
right.
Yeah.
So that my question was that the question is does that actually is that telling us that all clusters are at some level interacting, or at low frequencies what is going on? That how would you replace that plot into a new kind of relation?
Okay, yeah, this I think also touches to a previous question, sort of. Can you relate the amount of power maybe to the amount of the sort of a dynamical sort of estimate from X-rays? So if we remake this plot, that's currently sort of ongoing work with a larger sample, we indeed will see sort of that everything sort of get reds in this plot. But for the maybe small fraction of 10-20%, the question is, okay, where are they located in the plots? Are they really the extremely relaxed clusters, maybe the sort of the ones which didn't undergo a merger over very long time scales, and that all the other ones are sort of maybe so there can be a time scale argument, right? Because the radio emission sort of maybe fades over time a little bit. Because if you look at time scale arguments, it should have fade away sort of in a 0.1, 0.2 gigayear. But it could also be another indication, and I think that's more likely, is that every cluster, of course, at some level is undergoing some merger event. I mean, the concept of a relaxed cluster doesn't really exist if you start looking in detail. So that these other cases we are picking up, in which we're not picked up at higher frequencies, are supposed to then mergers which are sort of minor merger, more like events. So that is then sort of the prediction. So if we look at if we remake this plot and look at the differences, then the difference should be caused by sort of the minor merger, sort of semi-relaxed cases. And that would then sort of indeed point to the fact that every cluster maybe, that is sort of a more sensitivity effect. And also if you go at lower frequencies, is that if you have turbulent reacceleration, if you have less efficient mergers, you have this cutoff frequencies, and these cutoffs are done around a gigahertz. So at higher frequencies, you only can see this energetic sort of events. And the lower energetic you only can pick up at low frequencies, because on average their spectra are steeper. But there's also a relation between sort of spectral index and sort of the energetics available. And because we're now at low frequencies, we sort of can pick this sort of lower energetic component, which is really steep and just doesn't show up at gigahertz frequency. Or, as what Ruta said, it could also be that what we are seeing is hadronic things. So that is also another possibility. So in the end, I think if we do this careful analysis, we can indeed sort of get the answer here. Is this related to dynamical states? So we just go deeper, less energetic? Or are we seeing a sort of constant hadronic component? Or can we maybe see a sort of also a time scale effect, that if we can model mergers and sort of tag time scales to these clusters to sort of see trends there? And I think, that can all, I think, be done with this sort of larger sample. So I expect that quite soon we'll have some sort of answers here. But for now, I think that you are right. It's mostly likely to the fact that there are less energetic mergers, and these just will show some radio emission at some point if you go deep. And we are going deep, so
so that's a lot to look forward to. I mean, Kandu has another question, but before that, unrelated question. You're reaching 50, you're doing this big survey at 50 megahertz, right? That's where Jupiter comes in. So I'm sure there's a huge number of people working on planets, finding planets in the LBA maps, right?
Currently, we have a lot of people looking at planet in the HBA maps, because these maps are further processed, and because we're looking often at Stokes V. Stokes V is like a very nice sort of thing to pick up strange circular polarized emission, of course, and planets are highly circular polarized. For example, Jupiter is crazily circular polarized.
Absolutely.
And what we're seeing there is a lot of, actually, a lot. We see stars there in some publication out there. We see brown dwarfs showing up, maybe planets, but we have not really gone to the LBA yet, except for a few works, because the calibration and the Stokes V is just started. So that's, of course, where we want to go. So yes, if you go to the 30, 50 megahertz range, that is where you expect to start seeing exoplanets if you can go deep enough. They really should show up, because Jupiter is sort of the brightest source in the sky at these frequencies, at least nearby. And they have very strange spectra because they're the synchrotron spectra. So yeah, if you're at this frequency, you should start seeing exoplanet if you go deep enough. That's of course the question, because you can put Jupiter at 10 parsec. It's still very faint. Yeah.
Yeah, absolutely. That's very exciting. Kandu had another question. Go ahead, Kandu.
No, sorry. I just see the original thing which you started out with was saying that the low frequencies for the older electrons which have lost the energy. So have you looked at even just the low redshift sample where you don't, where merger is over and then things have decayed? For example, both the radio emission has decayed at high frequency and the magnetic fields have decayed. So have you looked at, maybe you'll find low frequency radio halos in relaxed clusters then? Or is
yes, we look. Actually, I made the mistake. I said we see this low frequency because they have. It's because they have not lost their energy, and that's why we can still see them. So it's still sort of. That was my mistake. Actually, I said it already wrong. Yeah. So at low frequencies, we see the things which are still have their energy. That's why they're still bright. Yeah. So it's sort of.
fine.
We are indeed looking at lower redshift clusters. So far, for all the sort of more massive cases, we do see diffuse radio emission. So I have yet to come to an example of a sort of really relaxed cluster nearby which does not show diffuse radio emission. What we are looking at is sort of the really low mass ends, because maybe then we see clusters which do not show radio emission, and there you might expect to see sort of a steep sort of spectrum component, maybe, or some sort of halo which is not picked up at high frequencies. But for the normal low mass clusters, if they are nearby, so far I think every cluster we have looked up with high quality data does show some, I think, diffuse emission. So the cases where we don't see anything, they don't seem to exist. Usually it's the case that then the data was bad or something. So it seems everything sort of has diffuse emission. And I think if we see new radio halos which are sort of missed, then it will be most likely in sort of the lower mass clusters, this sort of range, because we do see hints that of radio emission in low mass clusters, I should say. So this is a bit of an open question because it's always hard to classify, but it does look like Lovar is detecting sort of emission in really in much lower masses than what people have found with GMRT and with the VLA. And the question is then, are these then halos with very steep spectra? Because that is what you expect if there's turbulent reacceleration ongoing. That we don't know yet, but that is sort of one of the goals also we're looking at. So can we uncover radio halos in sort of very low mass system? But for the typical low mass clusters, they always show something.
Okay, thanks. Thank you.
Yeah.
Thanks very much. Thanks. There seem to be no more questions. Thanks, Reinout. We've given you a good run. And what a spectacular talk. Come back and tell us more.